Okay, let's see. There was a question on the discussion board about the homework, and I just now replied to it. Let me pull up the homework real quick and comment on it. Do you know where? Oh, here it is. Okay. Did they, hey Yabo, did they re-image this computer or something? The STAT645 folder, I don't see it anymore. There was usually a STAT645 folder here.
Yeah, that's the problem. So go to desktop.
It won't let me. Oh, okay. Oh, there it is.
Yeah, something disappeared.
Huh.
I think it's here.
Ah.
I don't know why. But
Okay, thanks. So for the homework on number 1, you're working with those onset data. And I asked you to make a picture. Scatter plot with age on the horizontal axis and onset on the vertical axis, and do some color coding of the points. So I have in mind a picture like this one. We have a scatter plot, and I asked you to color code the points. So let's say green for prior equals 0, and red for prior equal 1. You can do that with code that I put on the discussion board. For example, if your data frame is named DTA, then by saying with DTA, I can now refer to all of its column names, all of its variables directly, just by calling their names. So we could do plot age versus onset. And then the part that was novel that you maybe hadn't seen yet is how to use the points function. When you did that first call with data plot, it would just be black open circles for every point. There are functions points, lines, and text that you can call after having created an initial plot to add additional annotation or features. So for example, here we could say points, age, where prior double equals 0, comma, onset, where prior equals 0. And then I could specify color equals what we want. In this case, we'll do green. That will overlay a green dot on all the black dots for which prior equals 0. So you can repeat that for prior equal 1 to get red dots for prior equal 1. What I was going to do today in terms of covering content is talk about Bayesian statistics, Bayesian inference. I uploaded just a few slides for us to look at called Bayes. And I uploaded a script for us to play with. So under Notes, look at Bayes, and under Scripts, look at billiards.r. Let's start with the notes. Okay, we know how to do statistical inference a little bit now. It's all about sampling distributions so far. Whether we do simulation-based or classical approaches, so far we're doing what's called frequentist statistics, and that is assuming that there's a fixed quantity that is the parameter of interest in the population. There is an actual fixed quantity that is average survival time of people with a particular disease, say. And using frequentist statistical thinking, we kind of largely do inductive reasoning. We ask, given the observations we have, the data we saw, what values of the parameter are consistent or likely for giving us these data? At the end of that kind of inference, we're always left with those kind of clunky interpretations of confidence intervals and p-values. If I have a confidence interval for mean survival time of 5 to 7 years, maybe, we don't get to say the probability that you'll live between 5 and 7 years is 0.95. That's not how we get to interpret confidence intervals. A confidence interval we just interpret as 95% of all intervals constructed like this will contain the truth. But it would be kind of nice to be able to say the other one. The probability that you have cancer is this. The probability you'll live this long is that kind of thing. Frequentist statistics does not enable that, and so you're left with the usual interpretations. 95% of all 95% confidence intervals will contain the truth. And with a hypothesis test, if you compute a p-value and reject if the p-value is less than 0.05, say, then your interpretation is I made a decision in such a way that the probability I would have made a type 1 error is no more than 0.05. But that, again, is not applicable to our specific test. We get to say, if you go do a test, say with the bootstrap, and compute a p-value, check if it's less than 0.05, what you're doing in that routine is guarding yourself to only make a type 1 error, incorrectly reject the null 5% of the time. So you get to say, I'm 95% confident in rejecting the null, for example, but you do not get to say the probability that the null hypothesis is true is 0.05 or whatever your p-value was. So now let's think about Bayesian inference. One nice bullet point summary of this is that it does allow us to make those types of probability statements. So let's learn about it. The Bayes approach builds off of Bayes' theorem, which is a basic probability result. So if we have, let me make this a little bit bigger. Consider two random variables, x and y. For right now, we're calling them discrete, but they could be continuous. Two random variables. Any random variable has a probability distribution function. For a discrete random variable, it's called a PMF. X and y have their own, what we could call marginal PMFs. Marginal in the sense that they only speak to those individual variables, not jointly or conditionally. But we can also define a conditional probability function. In the discrete case, again, it's a conditional PMF. And this is probability that once we have already observed x take a particular value, what is the probability or the distribution for y? Conditional on x, what's the distribution of y? And then Bayes' theorem works with those conditional probabilities. What it basically does, the big picture is, it allows us, when we have information of this form, if we have data that we can use to estimate this, for example, the distribution of y given x, then Bayes' theorem allows us to swap the ordering of the conditioning and speak instead about x in terms of y, or x conditional on y. This right here is an application of really just the definition of conditional probability. we said that we have two random variables, x and y, and we have marginal distribution for x, marginal for y, and we also have the conditional of y given x. Bayes' theorem says that the probability of x given y, a function of x, is y given x of y times a marginal probability of x divided by either an integral or a sum. So a normalizing constant in the bottom. I'll put integral. So integral of f of y given x, marginal of x given y, y given x. Data. Integral. Okay. So the main piece is the numerator that allows us to say this opposite conditioning is proportional to this product. So let me tell you why this is relevant to inference. Suppose we have data x1, x2, xn, and let's suppose they are independent and identically distributed from a normal distribution, mean mu, variance, sigma squared. And for now, let's suppose that sigma squared is known. We'll assume known so that there's only one parameter for us to worry about. This thing called a likelihood that we've been seeing, likelihood, in this case we would write it as a function of mu, is the product of the normal PDF evaluated at each of the xi. We write this as if it's a function of mu, but we can also think of it like a joint probability of observing our data, x1 through xn, for a value of the parameter, mu. For a given value of mu, all the likelihood is a joint probability function as a function of mu. So suppose we wanted to talk about the probability distribution of mu given the data that we saw. That's really what we want to do with inference. We want to take our data and make confident statements about a parameter. So this can be thrown into Bayes' theorem. F of mu given the data is equal to, I'm just going to say proportional to so I don't have to write the denominator. It is proportional to f of the data given the parameter, and then times, I need some distribution for mu. Mu, we're used to thinking of as a fixed quantity, an unknown quantity. Now we're going to treat it like it's a random variable. If I can come up with that f of mu, which we'll call a prior distribution, then I can apply Bayes' theorem and speak in terms of probabilities for the likely values of the parameter. In terms of Bayes' lingo, this here is the likelihood. This is called a prior, and then this is called a posterior. It's like prior to observing any data, we have some preliminary beliefs represented by f of mu. Those could be very vague beliefs, like average survival time among the people in this disease group. If we didn't want to be aggressive in pre-specifying, we could say, let the average survival time be uniformly distributed between 0 and 20. Give it a big range and let it be uniformly distributed to reflect very vague prior beliefs. Once we see data, if we're willing to assume a distribution, we have a likelihood. And once we have those two things, we can get a posterior. Suppose we had a posterior. I'll show you how to compute one in a moment, but suppose you have, based on that application of Bayes' theorem, you have a posterior distribution. Posterior of mu. Then that is a distribution, a probability distribution from mu, having seen our data. What is the probability that the average survival time is 5 years or more? Using a Bayesian approach, I would just estimate that as the area under the posterior distribution, which would allow us to say, we estimate, given our data, that the probability you'll live 5 years or more is actual number. Okay, back to the notes. This is Bayes' theorem, and here is a write-up of what I was just saying. So suppose we have a distribution. This is parametric as far as we know so far. We're specifying a distribution for our population. That's the likelihood. That's where we specify what the likelihood looks like. There is some unknown parameter theta in a distribution F. We obtain a random sample which gives us our likelihood. L of theta is just distribution of data given theta. If we're willing to treat theta as if it's a random variable, it's a little bit counterintuitive. You would think, it makes sense that there is a single average survival time of all people in this disease group, for example. If we just went and got all of them and measured how long they live, we would know that quantity. Think of it more of like an analytical strategy, a data and analytics strategy to allow the parameter to be random. If it's random, then it has a distribution, and we call the distribution of a parameter the prior, because it does not incorporate the data. It's just prior belief. Then the posterior distribution is what we had on the whiteboard. It's proportional to the likelihood times the prior. All right, now let's do an example and see what it gives us. How does this work? One of the nice things about Bayes' inference is that it reflects nicely the way that we go about learning in the real world. Often, we make decisions and choices based on imperfect knowledge. We're confident that this is the right direction to go, but maybe we don't know for certain. It's probably not the best example, but like when I'm writing code, in order to be 100% certain that there's no bugs in my code, it would take me a long time to write it and double check everything. So end up writing, and maybe there's a couple of question marks. Did I get that quotation mark ended at the top, or did I close that parentheses? I don't remember, but I think I did. I'm confident, and I keep going. But then you click enter, and you get an error. So then you need to update your beliefs with observed data. Here's another example. It's kind of a fun one. Suppose you are going to meet a colleague at a pool hall, so you're going to play billiards and talk business. You don't have much confidence in your billiard skills, and you've never played this person before, so you don't know what to expect in terms of who's going to win these games. Let's let our parameter of interest be P, the probability that you win any one game. Are you better than this person, in which case P is bigger than 0.5, or are you worse than this person, in which case P is less than 0.5? What we can do is specify a prior. If we're going to observe some data, which we are because we're about to play some games, we need a prior to enable Bayesian inference. Here is a possible prior that we might pick. P is actually a continuous number. It can be anything between 0 and 1. As a simple illustration of Bayes' inference, though, I'm going to only allow these 11 possible values for P. P is either 0 or 0.1 or 0.2 ... up to 1. And my prior beliefs are reflected in the second row here, G of P. My prior belief is that it is not the case that I cannot win a game against this player. And it's not possible either for me to win every single game against this player. There is some chance that I'll win. There is some chance that I'll lose. My prior probability that P is 0.1 is 0.1. Prior probability that P is 0.2 is 0.25, and so on. I have specified a prior distribution. Okay, and then what's going to happen is we're going to play 3 games, and we're going to win the first 3 games. Then what has happened to our beliefs? We can use Bayes' theorem to incorporate these data and update our beliefs. So we'll do that, and then we'll suppose we play 2 more games and we lose both of them. So now we have additional information yet again, and we'd like to update our beliefs yet again. Let's go to billiards.r. Okay.
So in this simulation, can you be like more quantitative in defining the win or loss? So when you are saying like we win 3 games in a row, like in the modeling, do you put like, oh, it's a complete win or it's like a close game, it's just a slightly win? I'm assuming like that will affect how your predicted outcome is, right?
Yeah, question was about can we be more quantitative in assessing the games? So if there was a sensible way for us to define a numeric score. I don't know that there is one for billiards, but yeah, if there was one, if there was a way to maybe score you on 0 to 100, maybe if you got bigger than 50, you won. Maybe it's defined that you won, and maybe if you broke. If the first shot you made, cleared the whole table, you get 100, and everywhere in between. So yeah, if you had numerical variables, Bayes' theorem would apply just fine. Okay, let me run a little bit here. The possible values of P, I wrote it down 2 different ways, just they're equivalent. It's 0, 0.1 up to 1. So here are the possible values of P that we're going to allow for. Okay. And here's my prior distribution. These are just the numbers that were in the slides. So we could maybe make a picture. Let's do a picture to visualize what we're saying with our prior. Here are the possible values of P, and here are the priors. And let's do points and connected line segments, just to guide the eye. So there's my prior belief. It reflects not so much confidence in my abilities, because my prior puts most probability over, at lower values of P. Okay, let's suppose that we win 3 games in a row. Let me go back to the whiteboard for a moment. In the billiards context, we win the first 3 games. In order to do Bayes, we need a likelihood and a prior. We've got our prior. What would we say is the likelihood? How would we define a likelihood when what we're doing is success-fail trials? 3 independent success-fail trials. We could say that x1 and x2 and x3, if these are zeros and ones, these can be viewed as an IID sample from the Bernoulli. Bernoulli is just like flipping a coin or doing a trial where there's some probability P of, quote, success, otherwise fail. If x1, x2, x3 are Bernoulli, the distribution of a Bernoulli is P to the x 1 minus P to the 1 minus x. So my likelihood would be product those up. For every success, the likelihood contribution is P. For every failure, the likelihood contribution is 1 minus P. In our case, since all of those 3 x's are 1, the likelihood is just P to the 3rd. So back here, here's the likelihood. We're saying we won, in the first 3 games, we won all 3. We saw x1 equal 1, x2 equal 1, x3 equal 1. The likelihood is product of the Bernoulli with P to the number of wins and 1 minus P to the number of failures. What we now have, we don't know what P is, but we evaluated the likelihood for a range of possible values of P. Now we could make a picture of the likelihoods. Looks like that. So these are like probabilities of 3 wins in a row when P is equal to, take your choice. That's the likelihood, but that doesn't completely represent what we believe now, because we had prior beliefs. So we would like to fold in these new data with our prior beliefs. And here's how I can do it. Posterior, after having won the first 3 games, is Bayes' theorem. Likelihood times prior divided by, with a discrete case, sum of likelihood times prior. The denominator, that sum, if you remember from Stats 101, that's what was called the law of total probability. And the denominator is what you get when you apply total probability. It's an addition, it's adding up all the unions or all the intersections of like 1 with pri. So law of total probability, you might want to look that up if it's fuzzy for you. So we have a posterior, and now let's make a picture. This picture is going to show us the prior next to the current posterior. We started out with the red. We updated our beliefs based on our awesome performance in the first 3 games, and now we're feeling pretty confident. Posterior distribution is this. So I would use this to say the probability that I'm going to only win half of my games is this number right here, 0.1 or so. And I've got a pretty big probability. I have a fair amount of probability out here for P bigger than 0.6. All right. What can you do with a prior or with a posterior? There's a couple of things we can do. Here's one thing I could do. What if I wanted to estimate the probability that I'm better than this person? What we could do is treating this like a probability distribution for p, just compute what's the probability that p is bigger than 0.5 under this distribution. That's what this is doing. Summing, or more generally integrating under the curve, will give us probabilities. My prior belief that I was better than this person was 0.2. After winning 3 in a row, it has gone up to 0.75. And then let's finish this. Suppose we win or lose the next 2 games. We lose the next 2 games. What do we do now? We have 2 options at this point. One is to treat, let me start down here actually. One is to treat the prior at this point, after having won the first 3 games, but before playing the next 2. We could treat our posterior beliefs after those first 3 games as now our prior beliefs. This is what we believe now, and we want to incorporate some additional data. So here I'm going to say set the prior equal to the posterior from the previous 3 games. And if I lost 2 games from this point, my likelihood would be p to the 0, 1 minus p to the 2. Then my new posterior would be likelihood times prior divided by sum of likelihood times prior. Doing it that way, like sequentially, observing some data, incorporating your prior with a likelihood to get a new posterior, and then starting from there as if you have a new prior, is equivalent to if we had said, after losing the next 2 games, if we had said, let's just combine our prior with now this full record, win, 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 loss, loss. If I did that, my prior is still what it was at the beginning. My likelihood is p to the 3, 1 minus p to the 2, because I'm representing all the 5 games, and then I could get my posterior. Let's do this one. I'll run this one, and we'll make a picture. Red was the prior. Blue was after sweeping the first 3 games. Green was after then losing 2 games. So green is reflecting overall a 3 out of 5 win rate is what we have observed after our 5 games. And again, if you ran this, you would see the exact same results, whether you process it sequentially or all at once. In your homework, you are dealing with a more of a real-world kind of example. So you have a clinical trial. Clinical trial is a study in a biomedical setting, the kind of thing that's done with pharmaceutical companies who want to develop a new medication or prescription. And it would not be unusual to have this kind of scenario where you're going to enroll a certain number of patients, and they are enrolled as they are encountered. You don't usually get a full 1,000 people on day 1. So maybe you're enrolling as you go, and statisticians in a randomized clinical trial would be monitoring the results for this kind of thing. And then it would make sense if you are, enrolling so many a month or something, to do an analysis at the end of this month. You could incorporate the data that you observed in this month to update your beliefs about the safety of the drug, and do that every month. Bayesian inference is handy with respect to incorporating beliefs with new data, with updated data. Okay. Let me go back to the slides for a second. Here's the picture that we made. And when it comes time to doing actual inference on the basis of a Bayesian approach, there are a couple of techniques that are analogous to the frequentist techniques of confidence intervals and p-values. Specifically, if you want an interval estimate, there are intervals, we call them credible intervals instead of confidence intervals. That's just to specify this is from a Bayesian paradigm. A Bayesian credible interval is an area under the posterior that captures the inner X%, whatever percentage you want. 95% credible interval, for example, would go out to here and out to here, such that 95% of the posterior is captured. And the nice thing about doing it this way, Bayesian, is that we could say the probability that mu, or let's do it this way, the probability that that interval contains mu equals 0.95. Credible intervals are interval estimates of your parameter. They're computed in a Bayesian way, and they enable pretty straightforward probabilistic interpretations. Credible intervals, and there's also a p-value or a hypothesis test analog. May go into it next week if we have time. One way to do a test is what's called a Bayes factor. And it's kind of like a likelihood-based approach where we might compare the likelihood under this model to the likelihood under that model. There are likelihood ratio tests for comparing likelihoods. Bayes factor is like that. Compare the posterior under this assumption to the posterior under that assumption and quantify how different they are. In modern sophisticated data analytics settings, like with big data sets, for example, it's capital big data, Bayesian methods are pretty widely used. They're very flexible and can be formulated in a hierarchical way in particular. So, for example, at a national laboratory in the US, they might have data on some kind of weapon, and they're going to use physics equations to represent the decay and the operating characteristics of the weapon as a machine, I guess. But at the same time, they have uncertainty that they know exists in the measurements they take. So you might have a physical model like a physics equation, but you might also have uncertainty and measurement error. And for characterizing uncertainty and measurement error, you may have, so I'll say physical model with parameters. And you can lay on top of that physical model an uncertainty model, a probability model, and you can lay beneath that even more. So that distribution of uncertainty and measurement error would have its own parameters. And we can allow for distributions on them as well. They're called hyperparameters. So you have basically a likelihood and a prior, but you might have multiple levels of priors. Once you start having that kind of model, this deriving the posterior distribution can become a lot harder. This was a super simple example of a posterior distribution. And in order to get it, we just manually implemented Bayes' theorem. Likelihood times prior divided by sum or integral of likelihood times prior. But we might have a really complicated regression model. Y is beta 0 plus beta 1, x plus beta 2 y or z plus error. And we might say beta 0 has a distribution, and beta 1 has a distribution. Beta 2. The epsilons have a distribution. Bayes is a way to write down a model and then put uncertainty onto it through prior distributions. When we have a more sophisticated model like this, getting the posterior distribution typically happens by not analytically deriving the posterior, but sampling from it. Okay? When we've done the bootstrap, one way to do statistical inference is to use resampling to be an approximation of a sampling distribution. If I want to do inference on a mean, maybe, and this is the sampling distribution of x bar, my statistic, one way to represent this distribution, if I didn't know the analytical form, would be to somehow take the big sample from it. If I don't know the sampling distribution, if at least I can approximate it by taking a big sample from it, then it's just as good as knowing that whole distribution. You can compute confidence intervals, you can compute probabilities and p-values. That red histogram is something we could get via bootstrap. So the bootstrap is analogous to what we're about to do, because we're saying I want to know a sampling distribution, but the best I can do is generate a bunch of random samples from it. In the Bayes context, if we have a posterior, if we can't solve analytically for what the posterior is, if we can just sample from it. So there is a sophisticated way to sample from posterior distributions. And generally, what it's called is MCMC, Markov chain Monte Carlo. And this is kind of analogous to the bootstrap in that we're just going to do some random number generation in such a way that it will give me samples from the posterior. If I have a big pile of draws from the posterior and I wanted to compute this probability that mu is between A and B, if I don't know the formula for this, I can't compute the integral directly. But if I do have a huge pile of draws from the posterior, I can just compute a proportion. What proportion of the posterior draws were between A and B? We're not going to get into MCMC in this class. It requires some specialty, I guess, in implementing it. I don't know, maybe we will. We'll see. There are some built-in functions in R that make this reasonably easy to use. So I'll see if I could come up with some examples that we could use for like a proper MCMC implementation for a Bayes model. Okay, are there questions about Bayesian inference? The example in your homework is really simple. It's analogous to the Billiards example. So if you need help in implementing it, see the Billiards example. Let me show you one more thing, by the way, in the Billiards example. We started out with saying, let's let P be only these handful of values, 0, 0.1, 0.2. But P really is a continuous number. It could be any number between 0 and 1. So what I did at the bottom of this script was replace that discrete like coarse representation with continuous priors. One way to do a continuous prior on P is with the beta distribution, because beta works with values between 0 and 1. Here's one beta that's flat between 0 and 1. If I didn't want to make any presumptions about the values of P, if I just wanted to let the data decide completely, I could use what's called a non-informative prior. This would be non-informative in the sense that I'm not placing really any additional weight anywhere. Every location is equally likely. Here's another beta. If you change the parameters of a beta, you get differently shaped distributions. If you put in 1.8 and 6 as the parameters to a beta, for example, this looks a lot like that pessimistic prior that we started with. So we could replace that coarse analysis at the beginning with a proper continuous prior distribution, in which case you can redo everything we did above. So we could compute a posterior as likelihood times prior divided by integrate likelihood times prior. Instead of summing, when I have a continuous prior, I would say I would need to integrate. And there is a function called integrate in R. So I could do this down below, replacing the likelihood sequence and the prior sequence with continuous analogs. All right, I'll end there if there's not any questions. Okay, have a good weekend. See you Monday.